in order for a reaction to occur, it is always start with the bond cleavage. Okay, and then the organic compound, they are the compound that form through covalent bond. They are covalent molecule. Okay, that is why we talk about the covalent bond cleavage. So it is either occur in the homolytic fission or homolysis or homolytic cleavage. Okay, they are the same. Cleavage, fission, lysis. Okay, they are the same. Okay, it's either it is cleaved homolytically or heterolytically. Okay, so let's look at to homolysis. Okay, cleavage. Okay, if you look at to here, regardless of how many steps that we have in a reaction, okay, there are only two ways to break the bond. Okay, it's either the bond, the electron in the bond are divided equally, or the electron is divided unequally between the two atoms of the bond. Okay, so let's look at to if the shared electron are divided equally. Okay, we call the cleavage as the homolytic cleavage, or it is also known as the homolysis. Okay, so example is given here when we have a molecule of AB. Okay, AB, then when it is undergo homolysis, okay, or homolytic cleavage, okay, the shared electron are divided equally between these two atoms, A and B. Okay, so we know that in one covalent bond, they are sharing two electrons, right? A pair of electrons. So when we said that they divide the electron equally, okay, means that each atom will get one electron. Okay, that is why the product of this homolysis is A with one electron, B with one electron. Okay, or what we call it as the free radical of A and free radical of B. Okay, that's the product of the homolysis. Okay, as for the heterolysis or heterolytic cleavage, okay, the electron are divided unequally. Okay, in which only one atom, okay, that will get both of the shared electron. Okay, example is here. Okay, we have a bond that is formed between A and B. Okay, if let's say B is more electronegative than A, so that it will produce A plus and B minus, in which both of the shared electron here goes to B. Okay, that is why the product is A plus and B minus. However, if let's say A is the one that is more electronegative, so that A is the one that will receive both of the shared electron during this heterolytic cleavage. So that A will turns to A minus and then B will turns to B plus. Okay, both of these two processes, homolysis and heterolysis, okay, they require energy. To break any bond, always require energy. It's either homolytic cleavage or heterolytic cleavage. Okay, the difference between these two cleavage is just at the products that are formed. Okay, when we have a homolysis, it will produce uncharged reactive intermediates with unpaired electron, or what we call as the radical. Okay, as for the heterolysis, it will produce the charged intermediate. It's either the positive, okay, it will produce the positive species and the negative species. Okay, product of homolysis, uncharged, okay, but very reactive intermediate. Okay, as for the heterolysis, they are charged species. Okay, so to illustrate the movement of the electron, okay, in the homolysis, okay, since that we have one electron goes to A and one electron goes to B, okay, we are using the half-headed arrow, or what we call, sometimes it is called as a fish hook. Okay, half-headed arrow to show that only one atom goes to B, half-headed arrow to show that only one electron goes to B and one electron goes to A. However, if we have the heterolysis, okay, since that in this case, in this example that is given here, B is more electronegative than A, means that both of the shared electron will goes to B. We are using the full-headed arrow. Okay, so half-headed to show that only one electron goes to one side and the other side full-headed to show that both of the shared electron goes to one side. Okay, so this is important when you are showing, okay, the process. Okay, you have to make sure that you draw the correct arrow. Okay, if it is homolysis, half-headed, heterolysis, full-headed. Okay, so this is just a repetition. The homolysis will produce uncharged species, okay, with unpaired electron, okay, with the single electron that have no pair. Okay, and this product, okay, this product is known as a radical. Okay, this single unpaired electron is called as a radical. And these radicals are highly unstable, okay, because it is the atom that does not have a octet configuration. Okay, the atom that do not achieve an octet, they are unstable, okay, when we have a single electron. However, for the product of the heterolysis, okay, it will be carbocation ion or carbanion. Okay, just now we just talked about the positive ion and the negative ion. Okay, if the heterolysis cleavage, the heterolytic cleavage is occur in the organic compound, okay, we know that the organic compound are mainly, the main elements of the organic compound are carbon and hydrogen, right? So if the heterolytic cleavage is occur in this organic compound, okay, and the carbon are forming the positive ion, it will turn to carbocation ion, okay, while the negative one is a carbanion, okay, or carbanion. Okay, both of these two carbocation ion and carbanion, they are also unstable, okay, in which carbocation ion, okay, it has 6 electron, okay, while carbanion, okay, it will have a negative charge of the carbon, okay, it will have 8 electron lah. Okay, it will complete achieve octet. Okay, the carbocation ion do not achieve octet. Okay, so those that receive both of the shared electron octet, those that lost both of the shared electron akan incomplete octet. Okay, so if we focus on this structure, we start to have a carbon in the chain. Okay, just now it's just A and B. So this is one of the organic compound. We assume that we have a C that is attached to Z atom, any atom. Okay, and if it is undergo homolytic cleavage, okay, so that the product will be carbon radical and also Z radical. Okay, both of these two will receive 1 electron. Okay, however, for the heterolysis, okay, if let's say Z is more electronegative than this carbon, okay, example, if let's say we have a chlorine here or fluorine here, okay, so it will mix both of the shared electron goes to the Z, then it will mix Z turns to Z minus, and the carbon turns to C plus, or what we call as a carbocation. Okay, however, if let's say carbon is the one that is more electronegative than the Z. So carbon receive both of the shared electron. So due to that carbon, this carbon will turns to carbanion. Okay, and the Z turns to Z plus. Okay, so the product of these homolysis and heterolysis are, okay, radical, free radical for homo, okay, carbocation and carbanion. Okay, so if we look at to these two, radical and carbocation ion, okay, both of the carbon do not achieve octet. Okay, as for this, obviously that it has only 7 electron around it. Okay, so it is not achieve octet. Same goes with the carbocation ion that have only 6 electron around it. Only carbanion, okay, that achieve octet. However, it is still negative species. Okay, so due to that, okay, radicals, free radicals and also carbocation ion are also known as the electrophile. Okay, for those that already have the textbook, okay, you can look at to your textbook. Okay, search for the electrophile, okay, and also nucleophile. Okay, so these two are under electrophile because they contain an electron deficient carbon. Okay, any species that are deficient in electron, okay, they will turn to electrophile. Okay, electrophile means electron lover. They are looking for the electron in order for them to achieve octet. Okay, because when they are not octet, they are unstable. Okay, so how to become a stable is by looking the electron. Okay, so they are electrophile. As for this carbanion, okay, it is categorized as nucleophile. Okay, nucleon lover because they contain a carbon with the lone pairs. Okay, those that have extra in electron, they will be looking for those that are lack in electron. Okay, that is why the name is nucleophile. Remember nucleon? Okay, what we have is the positive species at the nucleus. Remember the nucleus of an atom consists of the proton and also proton and neutron, right? Remember your atom's structure? Okay, proton is the positive species. So that this carbanion, they will be looking to the positive species or those that lack in electron, that deficient in electron. Okay, so if we look at to the example that is given here, okay, we have a carbon at the center. Okay, we have a carbon, 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 carbon. Remember the skeletal structure? Okay, here will be CH3. I try to expand it for you. Okay, so we have to show the cleavage that is occur here. Okay, between the carbon and the hydroxyl group. So we know that oxygen is more electronegative than carbon, right? That is why the shared electron here, okay, will goes to the hydroxyl group. It will mix carbon turns to carbocation. Okay, and hydroxyl turns to OH minus. Okay, then another example down here, the bond between carbon and lithium. We know that lithium is an atom, right? This is more electropositive, so that the carbon is more electronegative. So both of the shared electron will goes to the carbon. Okay, it will mix, carbon turns to carbanion, okay, in this process, and lithium turns to the Li plus. Okay, if we have the heterolytic cleavage, you can use the full-headed arrow. If we have a homolysis, okay, or homolytic cleavage, use the half-headed arrow. Okay, as for this, okay, the movement of the electron, okay, when we have the product, okay, of the carbocation here, okay, the product of the carbocation here, it means that, okay, this cleavage occur, the cleavage that is occur is the heterolytic cleavage. Okay, heterolytic cleavage occur so that the shared electron will goes to the nitrogen. Okay, it will mix this carbon turns to the carbocation. Okay, and then the N2 turns to the N2 minus. As for the case that is happen in this hydrogen peroxide, H2O2, okay, the cleavage is occur between these two atoms of oxygen. Of course, that when we have a same atom, they have the same electronegativity. Okay, so the electron need to be shared, need to be divided equally between these two oxygen atoms. So homolysis occur. So we are using the half-headed arrow here so that it will produce two radicals of OH. Okay, and then this is the bond formation when we have the negative Br, okay, Br minus or bromide, okay, that is reacted with this carbocation. Okay, so the bromide will attack, okay, carbocation and they are forming the new bond between them. Okay, we are using this full-headed arrow because bromine is using both of its lone pair.